Hello, welcome all of you. My name is Attila Laszlo, and we have a presentation about the experimental study on rotational restraint provided by sandwich panels at elevated temperature. Our co-authors are Laszlo Horvath and Lendvai, and we are from the Budapest University of Technology and Economics. I would like to show you a short introduction, which is a kind of a feature review, where we talk about the rotational restraints of panels to the main members. There was some research in 2001 when they ignored this kind of restraint effect of the panels to the main members, but later there were other researches as well, and in 2008 they investigated this kind of rotational stiffness, but the higher limit was out of scope of that research. So our goal was to how to deal with the fire effect on this kind of rotational restraining effect. So we had a RFCS project. The acronym was STOPFI, where we did an experimental investigation of the components of the joint of the sandwich panels and the steel members. We, in this particular research, we wanted to define the rotational stiffness at ambient and elevated temperature as well. We would like to use this information to validate finite element models and define the experimental stiffnesses and the failure loads as well. So the design method, we would like to use the ECCS recommendation, but what is new in this case, the C component here is dependent on the temperature, where T is the temperature in this case. You can see here the test setup. Here we have two panels. Here are the main member, which was on I section. We have two sandwich panels on the left and the right side. We had one screw through the panel and the flange, and we applied the rotation with an eccentric tensional load to be able to rotate the main member, the I section. We analyzed the various panels. There were two types with two thicknesses, and we applied various temperatures as well, from ambient temperature to 600 Celsius as well. This kind of temperature was reached by ceramic heating pads. You can see on the right side a pad and the application of the pads. We applied it on the sandwich panels, and we assumed that the steel member were considered as a higher protected section, so we applied a lower temperature there on the eye section as well. During the test, we applied plenty of temperature sensors. You can see the dots here inside, outside of the panels, and the eye section as well. And of course, we measure the rotation, the axial force, which goes the horizontal movement and the displacement as well. You can see the main failure modes here. At some point in the test, when we have a higher temperature, we have seen some kind of lamination of the facing of the sandwich panels. You can see the deformation of the two panels during the rotation as well, and you can see the bent part of the facing of the sandwich panels as well, and of course we have a very large deformation and the screws as well. You can see some temperature curves according to the time. We applied at the specific heating rate, and we have elevated the temperature at the specific value that we defined at the beginning of the test, and after that we reached that temperature, we carried out the experimental test and the load. So the failure mode, we had no experience with a screw breaking or kind of rupture, but we see a screw hole elongation, and of course the local buckling deformations on the panels. Actually on all kind of tested temperature. In the slide you can see the horizontal moment and the rotation curves at various temperatures value, from the blue to the red one. Those were the ambient temperature on the top curve, and here are from the high blue to the dark blue. You can see the effect of the elevated temperature on the rotational stiffnesses. What we applied and what we used that during the evaluation of the test results is that we measured the rotations until 0.08 radian. You can see the evaluation method. As I mentioned, the assumed rotation was 0.08 radian, and we defined a simplified linear curve until that point, and this is how we define the rotational stiffnesses. You can see the actual spring stiffness values in the tables, and on the last column you can see the degradation of this kind of stiffness at different temperatures values, and for these two kind of panels what we used for the test value. So as a short summary, we had an experimental testing program in the name of the HubFib project, and we used mineral wool panels with two thicknesses, 100 and 230 millimeter height. We had a special arrangement of the test to be able to define the rotational stiffness, and we applied ambient and elevated temperature during the test values, and we defined the degradation of the stiffness according to this kind of elevated temperatures as well. So the basic idea in the next step, which was part of the project, define the design rules and guidance how to design this kind of steel members as well. And you can see here the project name, and with thanks for the support, for financial support for the experimental testing program. Thank you for your kind attention. If you have questions, please don't hesitate to ask. Thank you.